Okay, today we're going to continue with example 13. So example 13 wants to identify the rate determining step or the slow step, which I believe is already given to you in the notes. I didn't realize that the answer is there. Sorry?
Sorry, miss.
Oh, hi. What were you saying, Lim? Sorry.
Sorry, miss. I was stretching.
Oh, okay. Thank you for joining. Right, example 13. The question wants us to identify the rate determining step or the slow step, which we have learned from the last video that you have watched. We can connect the rate equation with the mechanism. We can find the rate determining step, which is the slow step, based on the rate equation. We also know what an intermediate is. Later on, I will explain what a catalyst is. Catalyst and intermediate, easy to get them mixed up. Right, so this is a reaction of a propane with bromine under aqueous condition, under alkaline condition. That's why you've got the hydroxide ions. If you are given the rate equation, what the rate equation can tell us is that our slow step contains these two species, which is the hydroxide ion and the propanone. If you look at the equation, the balanced chemical equation, which is this one, there are three species, three reactants species, and it makes you think that, well, we've got propane, we've got hydroxide, but not bromine. Okay, so if bromine doesn't appear in your rate equation, we say that, well, bromine is most probably zero order. Yeah, the concentration of bromine raised to the power of 0, which is just 1, and it doesn't appear in the rate equation. And the answer is here already. Okay, the mechanism, there are two steps to the mechanism of this reaction. The mechanism shows us in details how the bonds are broken and how the bonds are being formed to get from the reactants to the products. So if you look at the rate equation, we've got the propane and we've got the hydroxide ions, and this confirms that step 1 is the slow step or the rate determining step. And I think no further explanation is needed, but I do want you to learn how to support your answer or how to explain if the question in the exam asks you to explain why have you concluded that step 1 is the rate determining step. So from the rate equation, okay, please copy this down. It can be deduced that the two species, deduced cannot spell, deduced, oh gosh. That propane, CH2, CH3, and hydroxide are involved in the rate determining step and not bromine. So step 1 of the mechanism is the slow rate determining step. Okay, so since the next question I will be looking at intermediate and catalyst, I would just like to point out that our intermediates are species that does not appear in the chemical equation. It does not appear in the rate equation, but it only appears in the mechanism. But even so, intermediates only exist for a short period of time. Intermediate produce, and later on in step 2, intermediate is being consumed. That's why you don't see it in the overall equation. Okay, if you remember how I can relate the mechanisms to the overall equation, if I add step 1 and step 2, all my reactants added together and all my products added together, and you can see that I have intermediate on both sides, okay, at the same amount, 1 molecule of intermediate on the left and 1 molecule of intermediate on the right, so they can cancel out. Okay, so that's how you identify intermediate. They are produced, but they only lived for a short while because it will then be immediately consumed. Okay, next question is to identify intermediates and catalysts. So when a rate equation includes a species that is not part of the chemical reaction equation, then this species is a catalyst. Now, this is not a great definition for catalyst because intermediate also doesn't appear in the chemical equation. Okay, so I will show you the best definition or the best way to differentiate between the catalyst and the intermediate. But first, I would just like to go through this reaction quickly. This is a ketone, a butanone. Okay, so don't forget your organic chemistry friend. Butanone falls under the ketone family, reacts with iodine to form the product and the hydrogen iodide. And this is the balanced chemical equation, and it is made up of 4-step mechanism. Okay, the mechanism involves 4 steps. The rate equation is also given to you, and rate is equals to K rate constant times the concentration of the butanone times by the concentration of the hydrogen ions. Now, if you look at the mechanism, it suggests that step 2 is the slow rate determining step. Okay, and your rate equation should focus on this step. However, the intermediates doesn't appear in your rate equation. The reason for this is because intermediate in general are not written down in the rate equation. Okay, so you cannot write down intermediate K times the concentration of intermediate. So what you can do is you go back 1 step and see what makes up the intermediate. Okay, so this is intermediate being consumed, and that intermediate came from step 1 actually. Intermediate produced, and later in step 2 it is immediately consumed. But more important is we want to know what makes up the intermediate. Okay, the intermediate is made up of the butanone and the hydrogen ion. So it is easy to get confused with which one is the rate determining step. Okay, if you look at the rate equation, butanone and hydrogen plus, so you see butanone, hydrogen plus, you may be tempted to think that step 1 is the slow rate determining step, but it isn't. Okay, it is not. So that's why I guess for this question, they tell us which one is the, they tell us the speed of each step in the mechanism. Okay, so why we have butanone and hydrogen ions is because CH3, CH2, COCH3, and H plus make up the intermediate. Therefore, they appear on the rate equation. Okay, step 2 is still the rate determining step. Okay. Right. So sometimes, okay, in some reactions, since the rate equation involves the species in the step 1, they would just say step 1 as the rate determining step or the slow step, okay, which is it's technically not wrong because that's what appears on the rate equation, okay. But if you are given a question in the exam, they either have a definite slow step, or they will accept either one of the answer, okay. So they will accept step 1 as the rate determining step, or you say step 2 as the rate determining step. But the main point is that intermediates will not be included in your rate equation, okay. So you notice that H plus is not in the equation as well, okay. And this suggests that H plus may have been a catalyst. H plus is a catalyst because it doesn't appear on the chemical equation, but it appears on the rate equation. Okay, so that's one major difference between catalyst and intermediate. Catalyst can be on the rate equation, but intermediate cannot be on the rate equation. So I will identify my catalyst. Another thing about catalyst is that it is not produced in the reaction. It is something that we supply or we provided at the start of the reaction. And if you remember catalyst, one criteria of a catalyst is that it stays unchanged at the end of the reaction. Yeah, actually, more accurately, it's not that it stays unchanged, it gets consumed, but it is being regenerated. Okay, so you used up the catalyst, but you reform the same catalyst at the end of the reaction. Okay, so catalyst regenerated. Okay, so the main difference between a catalyst and an intermediate is this chemical equation. Chemical equation is the balance equation, whereas rate equation is, well, the one that contains the rate constant. Okay, so for catalyst, it does not appear on the chemical equation, but it can appear on the rate equation, whereas intermediate does not appear on either one. Sorry, that should be a cancel. Okay, it will not be on the chemical equation. It will also not be on the rate equation. So that's the main difference. Okay, if you don't remember that, you can always examine the mechanism. Is there anything new that you are producing in the mechanism and then later on it is being used up? Then that suggests it is an intermediate. And I think that's all for example 14 that I want to highlight. Let's see. Okay. Oh, okay. Sorry, my bad. Step 1 cannot be the rate determining step. It has to be step 2. Okay. Step 1 cannot be the rate determining step. It has to be step 2. I was reading a different question just now. Right, when you are done with this, please let me know because I will then move on. Thank you, Abby. I will then move on to the next part and the last part of this topic, which is catalysis. Okay, so catalysis does not involve any calculation. It's mostly description and things for you to just memorize. So I'll go really fast, but at the same time, I'll also try to highlight the important things that you would need for the exam. Okay, so explain that catalysts can be homogeneous and heterogeneous. Homo and hetero here is used in the same context as you would in your everyday life. Hetero means different, okay? Different phase to the reactants. Homo means the same phase. Now, what do we mean by phase here? Phase is not the same as state, okay? For example, oil and water, both of them are liquid state, correct? But these two are different phase because they are separated by layer, okay? Layer 1, which is the water, layer 2, which is the oil, right? If it's different state, of course, confirm it's different phase, okay? But if it's the same phase, you have to check again, are they in a different, if they are in the same state, you have to check again if they are the same phase or not, right? So what do I mean by this different phase and same phase? The catalyst is in a different phase from the reactants. An example of a heterogeneous catalyst is when you have your reactants, gases, Haber process, yeah, you have your nitrogen reacting with hydrogen gas in the presence of an iron metal catalyst. So your catalyst here is a solid where your reactants are gas state. Homogeneous catalyst is when your reactants and your catalyst are in the same state. For example, your reactants are aqueous solution. Okay, for example, then your catalyst would also be in aqueous solution. We'll look at the example. So heterogeneous catalyst often involves gaseous molecules reacting at the surface of a solid catalyst. You need to learn, memorize the mode of action of a heterogeneous catalyst. We're going to look at the heterogeneous catalyst first. There are three important steps in this heterogeneous catalyst. The first one is what we call adsorption. Make sure you don't confuse this with absorption. Absorption is when you absorb, when something passes through or goes inside like a sponge. Adsorption is that the reactants only stick on the surface of the solid, for example. Okay, so adsorption is like sticking on the surface. Second step is what we call the reaction. Of course, reaction, bond breaking, bond forming to form the products. And then the last step is the desorption, which is the opposite of adsorption. Desorption means unsticking. Okay, right. The first example that we're going to look at is the iron in the Haber process. Now, if you look at this example, there are 5 steps, but really the important major steps is the step 2, 3, and 4. Okay, first step, diffusion. Of course, you need the reactants to move to the catalyst. So since we're looking at the Haber process, we have our hydrogen molecule and nitrogen molecule moving closer to the catalyst. So that's what diffusion is. The second step, which is our first important step, is the adsorption. We have the hydrogen molecules and the nitrogen molecules sticking onto the surface of the iron. Now, what makes them stick is the intermolecular force of attraction. Okay, this force of attraction must be strong enough to break the covalent bonds within nitrogen and hydrogen molecule. So if you look at the reaction of the formation of ammonia, we have nitrogen molecule and hydrogen molecule to form NH3. Okay, for this reaction to happen, of course, you must break down the nitrogen molecules first to release the nitrogen atoms, and then you break down the hydrogen-hydrogen bonds to release the hydrogen atoms so that they can form a new bond between nitrogen and hydrogen. Okay, so the force must be enough to break, but also the force of sticking must be weak. So I'm talking about two different forces here. Okay, strong enough to break the bond in the molecule, but weak enough, this force of attraction, the glue that sticks the molecule or the atoms to the surface, must be relatively not too weak, okay, just right, so that it sticks during adsorption and we can release it easily during desorption. Okay, because if the glue is too strong, then the desorption process would be difficult. Okay, so you just need the right amount of force of attraction. Okay, the third step, which is the second important step, the reaction, is when the atoms, so we assume that the bonds have been broken already. So this is where a new bond is being formed. That's where you form the products. Hydrogen atom will form a new bond with nitrogen atom, and then they form an NH3. Once product is formed, the fourth step, or the last important step, is called the desorption. It's the opposite to adsorption. You release, okay? You break the glue, you unglue the product molecule to the catalyst surface. And lastly, the product diffuse away. Okay, so you can see that step 1 and step 5 is not so major. It's all about the movement of reactants and the movement of products. The most important thing is the step 2, step 3, and step 4. Okay, adsorption, reaction, and desorption. All right, we're going to use these 3 modes of action in the catalytic removal of oxides of nitrogen in car exhaust. So this is sometimes called a catalytic converter. Basically, inside the car, there is some metal, okay, there's a system which converts all the harmful gases that are released from the car into a less harmful ones, okay? So if you release carbon monoxide and oxides of nitrogen, whether it's nitrogen monoxide, nitrogen dioxide, NO, basically anything NO, then we use the platinum or palladium, PD, or RH metal, one of them, as a catalyst. Okay, so you can see that these are gases and your catalyst is a solid. And then you convert them into a less harmful gas. Carbon dioxide is, well, debatable. In the long run, it could potentially be a hazard to the environment, but at least, you know, we don't die immediately when we breathe in carbon dioxide. And nitrogen is also relatively inert. Another thing that I want to point out is that these metals, these catalysts, usually have a honeycomb structure. The reason for this is they want to increase the surface area of the catalyst so that more reactants can adsorb onto the surface. Okay. Right, the diagram is actually not looking at the reaction of carbon monoxide and oxides of nitrogen, but it works, okay? You imagine you have a palladium catalyst, and then your carbon monoxide and nitrogen monoxide adsorb onto the surface, and then bond breaking, bond making is happening here. And then once you get the product, you release the product, or we call the desorption stage. Okay, so the first stage is adsorption, where the nitrogen oxide or oxides of nitrogen, NO, and carbon monoxide will adsorb or will stick onto the surface of the catalyst, whether we use platinum or palladium or RH. Okay, so please copy this down onto your notes. It's actually pretty straightforward as long as you remember these 3 steps. And then the second step would be where the reaction is happening. Okay, so you first have to break the bonds of your reactants, and then you form the new bonds to form the products. Okay, please let me know when you're done copying this down. I will then move on to the second. Thank you. Second step is the reaction step. Okay, the weakening of the covalent bonds within NO and CO. Just the diagram is there. It's not actually for carbon monoxide and nitrogen oxides of nitrogen, but it's the same. The mechanism is the same. Once you break the bonds, you will have atoms on the surface of the catalyst. You bring the atoms close to each other. Okay, you bring nitrogen atom with another nitrogen atom to form a nitrogen molecule, N2, and then you bring the carbon and the oxygen molecule close to each other to form CO2. Once products are formed, then we move on to the next stage, which is called the desorption, and then the products just move away. Okay, done. Okay, so the desorption is the opposite of adsorption. It's the unsticking or the ungluing of the product molecule from the catalyst surface. Okay, so these 3 modes of action in a heterogeneous catalyst can be used for any type of heterogeneous catalyst. Of course, you just have to change the molecules and the atoms, but the mechanisms are the same. There's 3 important steps. You can add on the diffusion, okay, the diffusion of the reactants to the surface, or the diffusion of the products away from the catalyst after the reaction is done. And as you can see, the catalyst will stay unchanged. Okay, what if there's something happening onto the catalyst, which is what we call the catalyst poisoning? Okay, and the next part is the catalyst poisoning. So when do we call a catalyst that has been poisoned? It is when we have a layer of lead or a layer of other chemical species that coats the catalyst. Okay, so you don't want any coating around your catalyst surface. You just want the metal on it in its original form. So if you have impurities coating it, then this is where we say the catalyst is poisoned, because we can no longer attach reactants onto the surface if there's a coating. And this is also the reason why we don't want our force of attraction of reactants to be too strong onto the catalyst, because once it's attached, it's difficult to remove and it stays there. That means the catalyst cannot function normally. Okay, so that's what we mean by catalyst poisoning. And we want to avoid catalyst poisoning, because then we can no longer use the catalyst for its normal function. Okay, next we are moving on to the homogeneous catalyst. Homogeneous catalyst, there is no mode of action. There's no this three steps, but for homogeneous catalyst, usually the exam question likes you to write down the equation. So if you're asking me, do you have to memorize the equation? Yes, I have seen a lot of questions where they like you to write down the equations. The first example is the nitrogen oxide acting as a catalyst in the oxidation of sulfur dioxide to sulfur trioxide. Oh, okay. Before we go on to that, Usually homogeneous catalysis often involves changes in oxidation number. So homogeneous catalyst would be a system of redox reaction where you have reduction, you also have oxidation. A good catalyst would be a transition metal. In the next topic, transition metal, you will see that transition metals have variable oxidation states. It can be oxidized or it can be reduced easily. Okay, yes, Fab, go ahead. Next, right, so this is what I want to look at, this atmospheric oxides of nitrogen and its relation to the acid rain. So first, we just want to know how we form sulfur dioxide. Basically, sulfur is found as a impurities in fossil fuels. So when you burn fossil fuels, the sulfur will have enough energy to react with oxygen, and then it forms sulfur dioxide. Okay, right. Sulfur dioxide on its own is not that harmful, actually. Okay, students always tend to make a mistake by saying that sulfur dioxide will dissolve in water to form the sulfuric acid that causes acid rain. No, you always miss this step. The first step is that your sulfur dioxide will be oxidized to sulfur trioxide first. Okay, so this is the oxidation process. It is the sulfur trioxide that is harmful to the environment because it dissolves easily in water. Okay, so it dissolves in water. I'll show you the equation later on. So that means if sulfur is oxidized, okay, so oxidation of sulfur, your catalyst is NO2 here, nitrogen dioxide, and that means your nitrogen will be reduced to nitrogen monoxide. Okay, reduction of nitrogen here. Okay, so you can see that the catalyst has changed into nitrogen monoxide. We know that for a catalyst, they stay unchanged at the end of the reaction, or they are being reformed or regenerated. No problem, because nitrogen monoxide is easily reoxidized back to the NO2 in the presence of oxygen, which is everywhere in the surrounding. Okay, so nitrogen monoxide is easily regenerated back to NO2, and then the whole process repeats. NO2 will oxidize SO2 to SO3, and then SO3 will dissolve in water. Okay, so this is another important equation that you need to learn. It's the oxidation of nitrogen monoxide with oxygen back to the original form of the catalyst, which is NO2. Right, so how does this oxidation redox reaction of sulfur and nitrogen contributes to acid rain? Okay, so this part is not the whole story, right? It is this one. So when the question asks you, what are the equations involved in the contribution of acid rain, do not write this down, okay? Because this is the last step. They usually want you to write down the redox equation. Here, how did you get sulfur trioxide in the first place? Okay, because sulfur trioxide does not happen readily in the environment. Okay, so it is when you have sulfur trioxide, you dissolve it in water and you form sulfuric acid, and this is the contribution to acid rain. Okay, so the earlier redox reactions are more important than this part. Okay, to be safe, you just include all the equations if you can remember them all. But I think it's, if you put in effort to memorize, because it's an easy 1 mark, 2 mark question sometimes. And that's done for the homogeneous catalyst for the atmospheric oxides of nitrogen and its contribution to acid rain. Not much of explanation, but equations are important. So we move on to the very last part of this topic, which is the second example of our homogeneous catalyst. It is a reaction between iodine and persulfate ion. Persulfate ion is also called a peroxidiosulfate. It has the formula of S2O8 2-. Okay, so persulfate is a strong oxidizing agent. However, in the reaction with iodide ion, this reaction, if it were to happen without a catalyst, is really, really slow. Okay, because you've got anion reacting with another anion. So what happens? They will repel. The anions will repel. Okay, but this is a common reaction to form sulfate and iodine. I'm pretty sure you have come across persulfate ions in your practical paper, one of the practicals that you have done. It involves the persulfate ions. So how can we accommodate to this reaction? We want this reaction to happen, but it cannot just happen if we leave the persulfate and the iodide ion. This is where your catalyst, homogeneous catalyst, comes in. Persulfate is in aqueous form. Iodide is also in aqueous form. Your catalyst will be a combination of Fe2 plus and Fe3 plus, which is also in the aqueous state. Okay, now I forgot to mention, since persulfate is a strong oxidizing agent, that means it gets reduced. Sulfur is reduced, and for the iodide to iodine, I is oxidized. Okay, so this is a redox reaction as well. So Fe2 plus and Fe3 plus acting as a catalyst will also facilitate this redox reaction. Okay, so since S is reduced, the catalyst needs to be oxidized. Since I is oxidized, the catalyst needs to be reduced. That's why you have this reduction and oxidation reaction. Okay, so again, iodine to iodide, that is an oxidation reaction. Your catalyst is reduced. You go from Fe3 plus to Fe2 plus. Don't forget to balance the equation. In the previous syllabus, I always tell students to not memorize the equation because they can work it out using your electrode potential value in the data booklet. You got the half equation of Fe3 plus and Fe2 plus. You also have the half equation of iodine to iodide. And as long as you balance the number of electrons, you just add them all up. Okay. In your case, it's risky to rely on the electrode potential values because I'm scared that they don't give you the whole table. They only give you a certain part of the electrode potential values, just the ones that you need. Okay, so it's risky to not memorize them. So that's the reduction of Fe3 plus to Fe2 plus. Now I want to look at the oxidation of Fe2 plus to Fe3 plus. So the catalyst is now being oxidized, and the persulfate to sulfate is reduction. Correct, right? Yeah, reduction. So the order of this reaction actually doesn't matter. Okay, so which one comes first? It doesn't matter. But the most important thing is that both of the equations combined will give you iodine and sulfate, which is the products of the reaction that we are interested in. Okay, so learn the equation, know which one is being oxidized, which one is being reduced. No further explanation is needed. You don't have to explain the three modes of action. Okay, the three modes of action: adsorption, reaction, and desorption, is only for heterogeneous catalysts. lastly, I will just want to point out the energy profile diagram. Okay, so the energy profile diagram of the reaction between the persulfate and the iodide to form sulfate and iodine. Okay, so you have the first graph here is the graph of an uncatalyzed reaction. When you let persulfate and iodide react with each other, yes, they can react, but it takes a long time for them to react. And you can see that the height of the activation energy is this. Okay, this is an exothermic reaction, and I will call this the EA of uncatalyzed reaction. So that much is the activation energy. Okay. When we use the catalyst, there are two humps. Okay, two hills, and each hill represents one reaction. Okay, reaction number one, and the second hill represents reaction number two. But even with two reactions, the activation energy is still lower than the activation energy of an uncatalyzed reaction. Okay, remembering that catalyst provides an alternative pathway with a lower activation energy. Okay, so it's worth understanding what's happening with this energy profile diagram. EA catalyst of reaction 1 and EA catalyst of reaction 2. Okay, and the energy of the reactants and products stay the same. You are only changing the activation energy and also providing a different route. Instead of going on the higher hill, you go to the lower hill, there's a rest, and then you go up a small hill, and then you end up at the same ending place. Okay, so this is the entropy or energy profile diagram of the reaction of persulfate with iodide, which is an exothermic reaction. Okay, you don't have to explain why there are two hills or two mountains. You just have to recognize that the activation energy of the catalyzed reaction is much lower than when the reaction is not catalyzed. Okay. All right. That is the end of this topic. So